Okay, YouTube, up until now we've looked at the definition of the trig functions, sine, cosine, and tangent, the reciprocals, as kind of a right triangle definition. In this video, what we're going to do is generalize a definition for the sine, cosine, or tangent of the reciprocals for any angle in standard position, so long as we know some point, say, on the terminal side of that angle. And so what we're basically going to be doing is taking our initial SOHCAHTOA, or right triangle understanding of this, and saying, look, if xy is some point on the terminal side of our angle, and let's let our angle be in standard position here, so our angle theta would lead from the positive x-axis. Basically, if we knew a point xy on the terminal side, we can always drop an altitude back down to the x-axis, or back up to the x-axis if you're an angle that terminates in either the third or the fourth quadrant. But basically what you're going to see here is, by knowing x and y immediately, we know that the value of the height of the triangle here is y, and this displacement in a width direction is x. And what we're going to do is we're going to label the hypotenuse with r. But the nice idea here is this. If you know this point xy on the terminal side, then we could say that the sine of this angle, using our SOHCAHTOA relationship, would be opposite over hypotenuse, or the y value of that point over the r value. Likewise, if we were to find the cosine of this, we would say adjacent over hypotenuse. We get x over r, where x is this x value at our point there. And then we say tangent. Tangent would be opposite over adjacent. In this case, with respect to theta, we'd say y over x. So the nice thing about this definition right here, and it's the same definition that you see placed over here. Likewise, one thing I want to point out is that the reciprocals over here, if we know that the sine, cosine, and tangent are y over r, and y over x respectively, where x is not 0, we say then cosecant, secant, and cotangent are respectively just r over y, r over x, and x over y, where we do not allow y to be 0 in either of these cases, and we don't allow x to be 0 in this case, because we don't want to divide by 0 and have an undefined value. So that being said, what we could say is, let's understand every single angle that we could draw in standard position as intersecting a circle of radius r at some point xy. So long as we know this point xy, though, on the terminal side, we should be able to use these definitions of the trig functions to go and evaluate for the trig function values at those angles. So one really quick thing I want to mention here is this. We must know a point xy on the terminal side. The stipulation to being able to find the trig values of a function of theta is knowing a point xy on the terminal side. And the reason why is because if we know x and y, then we know the two dimensions of our triangle that are the legs, and we can use those to go find the hypotenuse r. So let's recall that x squared plus y squared equals r squared in this right triangle here that has an x, y, and r set of dimensions. But essentially what we want to say is that r squared, if it's equal to x squared plus y squared, then we can say that r is always equal to the square root of x squared plus y squared. So this just means that we can use Pythagoras to go and find the value of r. And we want to make a little note here that the value of r is always positive. The value of r is always positive. And in terms of what r represents here, it is the radius of our circle. But we could say that r is the distance from our point xy to the origin 0, 0. So what I want to do here is use this new definition of these trig functions in order to go and find, say, the sine, cosine, and tangent of an angle theta in standard position, so long as I know this point -4,3 is on the terminal side. So what you're looking at in this particular example is an angle that is in standard position, meaning it leaves from the positive x-axis. And the first thing they've done is actually they've went and graphed -4, 3. So graphing -4, 3, you'll notice that they have an altitude drop down here from this point to the x-axis. But what we end up with is our right triangle right here. So I'm going to label the parts of this right triangle. As a matter of fact, we know x is -4, we know y is 3, and in this case we need to go find r. So what we're going to need to do is use Pythagoras here. We have 3 squared plus -4 squared is equal to r squared. So in this case, we're going to get 9 plus 16 is r squared, or that 25 is equal to r squared, or that our r value just is simply 5. So what I'm going to do here is just a suggestion. You can take it for what it's worth, but I always like to list our x value, our y value, and our r value. So we know r is a positive 5. We know that our y value here is a 3, and our x value is a negative 4. So what we're going to see here is this. Let's go ahead and set ourselves up. We have the sine of theta, the cosine of theta, and the tangent of the angle theta here. But we know that the sine value is by definition our y value over our r value, or opposite over hypotenuse here. So we would say our y value in this case is 3, our r value is 5. So the sine of this angle would be this 3 over this r value of 5, so 3 over 5. We look for cosine. Now cosine is x over r, and so we still have an r value or a radius value or a hypotenuse of 5. But in this case we have adjacent over hypotenuse, or x over r, so we get negative 4 over 5. So for the first time you're probably seeing a trig function that comes out to be negative in value. So let's go ahead and take a look for the tangent. Now tangent is y over x, or opposite over adjacent in this diagram up here. So we would say y over x, our y value is 3, our x value is negative 4, so we would just say negative 3/4. And in terms of getting the other three functions here, the interesting thing is we don't need to memorize them, we just need to compose these. And so here's what we have. The reciprocals of the original three values, 5/3. Now negative 5 over 4 and a negative 4 over 3. The idea is that if these are negative, then their reciprocals are negative also. So let's go ahead and take a look at another example of doing what we just did here, except for in this example we do not have an image that's already drawn for us here. So I know that I placed this somewhere. Let me go ahead and find this. So we have right here. So we'll just go ahead and borrow this. Sorry, thanks for being patient. I'll dig this open here, and we'll just copy and paste it in. Okay, so what we want to do in this particular instance is say that 8, negative 6 is a point on the terminal side of an angle theta that's drawn in standard position. So we want to find the values of the 6 trig functions of theta. So let's go ahead and do something really important first. Let's go ahead and sketch a picture of our angle. And so with respect to our angle, we know at least a point on the terminal side is positive 8 comma negative 6. So sketching this in here, let's go ahead and grab our pen tool. We would have positive 8, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's 8, and then we'll go 6 down. So we have 1, 2, 3, 4, negative 5. I'll just go negative 6 here. So we have this point, and what we're going to say is that our terminal side of our angle goes through this point right here. So here's our angle in standard position, and we're going to refer to this angle as theta. So from here, I would strongly recommend going ahead and labeling this point, because what we always want to do is drop down in altitude back to the x-axis and discover that we have a right triangle here. So in terms of the parts of this triangle, we know that the y value is negative 6 and the x value is 8. The only thing we don't know yet is the r value. So let's go ahead and dig out the value of r. We have 8 squared plus negative 6 squared is equal to r squared, or that 64 plus 36 is r squared. This is helpful because we get that r squared has a value of 100, or that r must be 10. And remember that we say that r is always positive. So with respect to this, let's go ahead and crank out our sine, cosine, and tangent here, and then we'll get our reciprocal functions. But remember that sine is y over r, so we have a y value. Let's list these out. X, y, r. We have a y value of negative 6, an x value of 8, and an r value of 10. So with respect to our y value over our r value, we get negative 6 over a positive 10. For cosine, x over r, we're going to end up with positive 8 over positive 10. And then for tangent here, we get y over x, which gives us a negative 6 over positive 8. So I will reciprocate these. One thing I do want to mention, though, is that if you can reduce a ratio, you probably ought to do that in the first place. So I'm going to go ahead and reduce all of these. And then what we're going to do is we're just going to say, well, then the cosecant of this angle must be negative 5 over 3, as that's the reciprocal of our sine. Likewise, the secant of this angle must be 5 over 4, and the cotangent of this angle theta here must be negative 4/3 here. And so what we're seeing here is a situation where two of our trig functions were negative and the other one was positive. But that's something that we've opened up the possibility of having now that we can have any point on the terminal side, and sometimes x and y are negative depending upon where you terminate. Cheers.